Today, now we're going to do pH and we're going to talk about acid dissociation constant in order to do our acid-base titration this afternoon. So the first thing, pH. pH. Does anyone know what pH actually is? Or could tell me what pH is? Alright, I'll just give you a definition for a start. So if you write this down, it's a measure. So pH is a measure of the hydrogen ion concentration in a solution. And it is defined as the negative logarithm of the hydrogen ion concentration. So that's a verbal. All you have to know is the actual equation, which says pH equals minus log of the H plus ion concentration. That's it. So, to give you an example, we're going to do the concentration of the pH of a HCl sample that has a concentration of 0.05 molar. So you'll need your calculators. Now, the first thing you have to realise is square brackets. Square brackets. Alana, do you know what square brackets mean?
Concentration.
Yes. So, if you see square brackets in chemistry around something, especially if it's around H+, it means concentration, not moles. It's moles per litre. Or molar, all the same thing, those things. So you cannot put just moles in there. You have to change moles to moles per litre, which can be very different. So you can see that when I'm giving you this to work out, the HCl is written as a concentration, not just moles, because you need to know how many moles in the liquid, how much liquid. So it's 0.05 molar. So pH, this is an example, is going to equal minus log of, and now you can use the round brackets because you're putting the actual concentration in, 0.05, and you plug that into your calculator, and what do you get? How do you do it? So you turn your calculator on, and then you put in 0.05, or you actually press log first on some calculators, log. You can put the minus in, but if you get a minus number, a minus comes a minus is a positive. So log 0.05 equals, and you'll see minus 1.3. Did everyone get that?
Yeah.
And then you times it by minus 1. A minus times a minus is a positive, so you end up with 1.3. 0, 1, 0, 2, blah, blah, blah. But if we're going to one decimal place, 1.3 is the pH. And what type of acidity level is that?
1 that's very acidic.
Very acidic. So it's probably HCl or some very strong acid. It's not going to be a weak acid like vinegar. It's going to be a strong acid. So 1.3. Alright, that's how you use it. If you want to turn pH back into the concentration of your acid, which sometimes you do want to do, you do the opposite, because logarithms, a log means to the base 10. So if you want to now find the H plus ion concentration from a pH of equal to 1.3, you say 10 to the power of minus 1.3. Try that. So and right, and you should get equals 4.05 molar. All right, so that's the first thing, how to work out pH from your hydrogen ion concentration and how to change pHs back into hydrogen ion concentration. So that. Now the other thing that I'm going to use this board for, let's squash it on in a different colour, is looking at what's called acid dissociation constant. Oops, that's not right. I'll say it. Dissociation. Tell me how to spell it. Dissociation. What have I done? Double S. I know how to spell this, but up here, I don't know how to spell it. Acid dissociation constant has a symbol K subscript A. Now I'm going to do a very brief account of this for year 11 because it's a topic in itself. The equilibrium is a topic in itself in year 12 and it takes a lot of description. But just very quickly, if this is a standard acid, any acid, so we can write any acid with a H and A is just standing for acid. So this is any acid. And we want to show that it dissociates, so it'd go into H plus and A minus. Do you agree? If this was any acid? Yeah? We're not putting the water into it, otherwise we could go HA plus water gives hydronium ion plus your A minus, couldn't we? Right? Okay, so this is the truncated version. Put the dates in. If we want to show how much the acid has dissociated, we can make a ratio over the products over the reactants. And that's essentially what an acid dissociation constant is. So Ka equals the concentration of the H plus ions raised to the power of whatever's in front of this. Now because this is already balanced, like the 1 to 1 to 1, there would be a little 1 up here, and we never write 1s in chemistry, but for the sake of you knowing what to do, if there was a 2 there, you would write it, would be squared. So we just write little 1s. So this is A minus 1 over the concentration of your acid, 1. Now if you're following, it's really a ratio of products, the product of the product amount, concentrations over the reactants. So it's telling you how much the acid is dissociating into its ions. Can you see that? So if you know the H plus ion value and you know that these are going to be equal in concentration, because they are, well, if this splits up, you're going to get the same amount of this as the same amount of this, aren't you? Then you can work out how much it has dissociated. Can you see that? I think so. It's hard for you to grasp all in one thing, but this is called the acid dissociation constant. And it's an indication of how weak your acid is. So you can see that if you haven't formed many ions, this number is going to be really low. The lower the Ka, the more it hasn't dissociated. So for example, acetic acid. Acetic acid, what is it? So for example, vinegar, Ka, I don't know what it is actually, I'm just going to pick something pretty low, 4 times 10 to the minus 4. Let's say it is that. That's telling you that hardly any of your acid has dissociated. And I'm going to show you how you can use it further on. So, I'm going to do this little example here, just to show you. So if you've got a very weak acid like we have with vinegar and you want to work out the pH, you have to take into consideration that it doesn't completely ionize. So here's an example of how to use it. So when we rearrange this formula here, we get H plus equals the square root of Ka and I haven't used C because, but it's the same thing, HA. Can you see that? Now the reason there's a square root in there is these would be the same. So we're saying, I've skipped a step. Okay, let's go and make this the subject here. H ions concentration would equal Ka times each side by this times HA divided by, well they're the same. So it'll be H squared. Can you see that? If they're the same concentration, you could write H plus squared equals that. Do you agree with that? And that's where you get down to here. Then if you want to get rid of this squared here, it's square root of that. So, why am I showing you that? Because if you've got a weak acid, you can still work out the pH. So what you do is you use their Ka and you use the concentration that you had to begin with. So if we had a vinegar solution, or I should say acetic acid because it's pure acetic acid, and it was 0.01 molar in concentration, and we know it's Ka, and let's assume it's this, it isn't, but let's assume it is, then we can work out the H plus, and once we can work out the H plus, we can work out the pH, can't we? So let's do that then. So for the example, for acetic acid at 0.01 molar, we have the H plus ion concentration going to be the square root of 4.0 times 10 to the minus 4 times our initial concentration of the acid, 0.01. And then you stick that into your calculator. Let's all do it so you know you can. And hopefully you agree with me. That would be handy. Did you get this? 002. Yes, hooray. Now put that into this formula over here and you can get the pH of your acid solution. pH equals that minus log of your 0.002, that can be rounded now, and what do you get? Did you get 2.7? What did you get?
I didn't write it.
Oh, hang on, what haven't I done? Oh, that's right. Did you get that?
Yeah.
Okay.
1 second.
So have this to tell you how weak it is, and you just did it normally, let's say it was an acetic acid and that's the concentration of your HCl, put that in to your pH. So this is if it was acetic at that particular concentration, but if it was HCl, you would just plug in the actual concentration of your hydrogen ions without the Ka and the square root part, and you would see that it is 0.01, and what do you get? What do you get? I've got two. 0.01 log, sorry, hang on. Log. Yeah, well, it's not much of a difference. However, I made this thing up, so maybe I didn't go far enough with how weak it is. You know, maybe this should be a small, but just to show you that this Ka tells you that this is a weaker acid, doesn't it? Because it's got a higher pH. So you can see how it works? Right, so that's important for, especially for Alana. Not so much for you guys, but you can use it if you want to. Alright, so that's that part. Now I'm going to show you the equipment for a titration. So I'm going to do a new board and we're going to keep that running. Going to try and do a new board. So, titrations, all right. Titration is a form of volumetric analysis. So using volumes of liquids to work out or solve a problem. So this is a way of finding out an unknown concentration using a known concentration. So the best way to explain this is to just use a common example of HCl, which is what you're going to be doing, plus sodium hydroxide. This is a neutralization reaction, isn't it? Acid plus a base gives, what does it give?
Salt and water.
Salt and water. There we are. Now, if you had, this is what has to happen, and will happen for you today. We're going to try and work out the concentration of our Coles vinegar. But in order to do that, we have to have a known that we can rely on. So because vinegar is an acid, we need to use a base to find out what it is according to this, if we want to use a volumetric analysis situation. So we use our sodium hydroxide, except sodium hydroxide reacts with carbon dioxide in the air. It's always changing, so it's not reliable. So you firstly have to standardize it with very stable hydrochloric acid. So that's why you start with this reaction first. So if I had a concentration of 1 molar HCl, and I don't know what this is, I think it's, let's say I think it's 1 molar, but I'm not sure because it could have changed overnight in the atmosphere, so we don't know what it is. We don't have to worry about that. We do have to worry about a balanced chemical equation. So this is a balanced chemical equation. It says 1 mole reacts with 1 mole. So stoichiometry you've done, and so you should understand the necessity of having a balanced chemical equation. So we know our hydrochloric acid. So what we're going to do is, I'm going to show you this in a minute. In the meantime, I'm just going to draw it. This is a burette, and we've got a conical flask. Now we always put our base in the burette to keep them always seasoned with base. So we're going to put the sodium hydroxide in there. And we fill it right up to 0. So it's full. And down here is full as well, below the tap. full of sodium hydroxide. And here is our acid, which we know what, so the base is the unknown, and it doesn't matter which way you put these. You can have the unknown in here, just for the sake of always keeping things the same, we put the base in the butyric 2Bs. Acid, HCl is the known. So, we're going to use a pipette, and there's certain volumes. This is a very accurate piece of glassware. It is 25 mils, and it has a very, very low error on it, something like 0.06. So you fill it up, it's not a normal, just it only holds 25, it measures only to 25, and you fill it up to that. The meniscus is in the bottom of the meniscus on that line, and then you'll get a very accurate 25 mils. That's a 25 mil pipette. And so you'll have 25 mils of your acid in here. So you write that up here. We've got our concentration of our known, and we've got the volume of our known as 25 mils, which we convert to litres straight away. Yes? We're going to work out our sodium hydroxide. So what we do, and this is what Stuart was talking about, is we put an indicator in here, phenolphthalein. Phenolphthalein has some interesting spelling. Hang on. Let me get it right for you. Phenolphthalein indicator is an indicator that is good for an acid-base reaction. It starts off clear and turns pink when the base gets to the neutralization point. So it's the drop that you want it to go the slightest pink, hence the white paper. So you drop it in, it's clear, 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 you're swirling, swirling. When the very drop that turns this pink is what's called the end point of the titration. End point of the titration. When the indicator changes colour. And let's say that we were dropping that in and it was, I don't know, the volume of 23.9 mils. That's what we recorded after doing it 3 times and averaging. Is it hot in here? And then we convert that to litres, so 0.0239. I'll show you now what to do. We can work out the concentration of our sodium hydroxide, and it's called standardising the sodium hydroxide. So, this equation, we really need to be concentrating for this. This equation is like a recipe. What it says is 1 mole, even though we don't use ones in chemistry, they're here. 1 mole of this reacts exactly with 1 mole of this to produce 1 mole of this and 1 mole of this. So if we know how many moles of this we have, we know how many moles of this we have. So, this is an aside. Moles equals, oh hang on, I think I'll do it the other way around. Concentration of something is measured in moles per litre, as you know. Moles over volume. Moles litre. Concentration is moles per litre, isn't it? So if we rearrange this equation, we get moles equals concentration times volume. Assumed knowledge at this stage of the proceedings. So, therefore, knowing that, moles equals concentration times volume. 1 times 0.025, which equals 0.025 moles. There. And one-to-one relationship means that there must be 0.025 moles here. So, by plugging the two we know into the concentration formula, C equals moles over volume, you get, because that's what this is, C, question mark, 0.025 over 0.0239, and you plug that into your calculator. Let's all do that so you know what we're doing this afternoon. 0.025 divided by 0.0239, and what do we get?
1.05.
Very good, molar. So, it wasn't one, it was that. And then, the second part of the, if we get up to it, if you guys don't get up, it doesn't matter. If we get up to it, the second part of the experiment this afternoon is to now use your standardized sodium hydroxide to find out what the vinegar is. So, I'll just write that for you, but we won't go too far because I want to show you the practicalities. So, and I'll repeat it this afternoon. So, once we've done this first step, step 2 would be sodium hydroxide, which you've now standardized and you know the concentration is 1.05 molar, plus your acetic acid, so CH3COOH, gives what's called sodium acetate. The sodium comes onto there and the hydrogen goes onto the other part to form water, H2O. So it's still a 1 to 1 to 1. Can you see what's happened? This has joined there, it's swapped with the hydrogen. So then you have a known there, you have a C that you don't know here and you're trying to find out. And if you put your vinegar now in here, and I can do this because we already have this on video, so we change this with great difficulty to, but it's exactly the same process, to the vinegar. And we do our titration, and let's say we want to know what it is. So we might get a titer, and it's called a titer. So if we drip this in, and we get 10.9 mils this time, that's called a titer. We can then work out, so the volume we've used to work out our unknown concentration is
25 mils.
10.9 mils this time, because you're going to an end point. It's a new acid.
Okay.
So the volume of our acid we know, and because we put the acid, the unknown in here again, we've got 25 mils. So this is where the 25 mils is, isn't it? This is where your vinegar is down here.
Oh, yeah.
We've used that. We've got the we've refilled this back up to 0. We've titrated and we've got a titer of 10.9 mils. So now we do exactly the same process. Let's practice it. So number of moles would equal 1.05 times 0.0109. Do that on your calculator and let me know. I'll race you.
0.011445.
0.011.
445.
Does everyone agree? Yes?
Yes.
Alright, that's number of moles. 1 to 1, so the number of moles must be the same, 0.011445. Therefore, concentration is going to be moles over volume, which is 0.011445 over our new volume, 0.025.
0.457.
4, 5,
78.
7, 8 molar. So it's half the strength about of our, which wouldn't be true, it'd be much less, but I just made these titles up. And really, from experience, so this is the concentration in moles per litre of your vinegar. You can then convert that to mass. I'll show you that when we go over to the lab, but moles per litre of our vinegar. In reality, your vinegar is so weak. Well, actually, that's not true. If we use 0.1 molar, I don't know what they've given us over there. Hang on, I might say over there. Yeah, we're using a 0.1. If we use 0.1 hydrochloric acid, no. If we use 0.1 sodium hydroxide, that's very dilute, and the vinegar is too strong. And you'd have to keep filling. You'd have to use all the way down to the bottom, and you still haven't had a colour change, and you'd have to refill it. So what we do is we dilute the vinegar by 10, a dilution factor of 10. So you take 10 mils of vinegar, bring it up to 100 exactly in one of those little volumetric flasks, and then you take 25 mils of a diluted sample. So that's what you do because we're using such dilute quantities. To fix that, you could use 1 molar instead of 0.1 molar, but we've got to go with what the prac has said and what they've given us this afternoon. So, handing over to here, and I could just, if you stay there, I can just turn this around. This is how you will set up your titration. So this is a retort stand, and this is a burette, and this is called a burette clamp. So they're nice, they hold 2, but we only need to hold 1. And you need to set it up so that you can put a conical flask under it, and once you've filled it up, you lower this so that the tip's in the conical flask, but you can still get it out easily. And this will go under so you can see your colour change. So essentially you sort of know what we've got to do because of how we explained it up there. So you'll fill your base that you're given, 0.1 molar sodium hydroxide right up to 0. The mistake that students make is the tap's off. That's not a mistake, that's good. Make sure the tap is off, otherwise it'll start streaming out the bottom while you're pouring in the top. You need to use a little one of these, and it forms a bit of a plug, so you need to hold it up slightly, otherwise you pour it in and it all comes gushing out. Have you ever had that happen? So if you hold it up a little bit, the air pressure can get out and it flows down. So you use the funnel to fill it up. The bottom of the meniscus has to be right on the 0. However, you want to fill it up past the 0 first, because what students forget to do is fill this part of the burette, and this is designed to measure every drop that leaves. So if you don't fill this part up, first of all it fills this part up and you're not getting an accurate reading. You want to know by displacement every drop that leaves this, don't you? So if this is empty, big error. So you fill it up past the 0, then with a waste beaker that you have, you let it run, you open it, and it's good practice for you to see how fast it flows out. You let it run down until the bottom of the meniscus is on there, and now that's full and that's on 0. Yes? Once you've done that, vinegar is going to go in here. Now you will have to dilute it by a factor of 10, and that's easy. Then you get your pipette and your bowl. There's a technique to using these. So this has got valves in it, so I'll just show you. A valve will fill it up, and you've got to leave them like this, otherwise they go nuts because it ruins them when they're flat. So when we're finished, make sure all the bulbs are blown up. You want to empty it, so you press the A and you squeeze all the air out of it, because that's how it's going to work. Then you pick up your pipette. These are very fragile, the necks break. I have seen a student go to put it in, it's a bit stiff, snapped off and gone through his hand. So you need to hold this up here and put that a little bit on. Another mistake students make is they wedge it sort of right, and then they can't get it off. You only need it to be slightly on the very tip and it'll work. So, just put it on, doesn't have to be thoroughly in there. And then, say this is your vinegar that you've diluted by a factor of 10. You want to draw it up so this end has to be underneath the solution at all time. If you're not concentrating, you lift it up, it's going to have all air bubbles. And you press this valve that fills it. So that's the same one, this middle one. So that's actually the one here that empties the bowl. The one at the top. The one in the middle will fill it. So it fills really fast here. Then when it gets to this bulbous section and you're not paying attention, it's so slow and you're looking around like this. And then it fills really fast here. So what happens is students who aren't paying attention, all the acid goes in here and it sticks all this together and ruins it because it's corrosive. So you've got to try and make sure you stop about here. Then with your eye down on eye level, you press the E, which empties it slightly, and you just want the meniscus to be on that. As soon as it is there, lift it up. It will lift up, it doesn't matter, you've got the right amount in there. And you put it into your conical flask. And I don't bother pressing the E, I just let it run out. And then these are calibrated, so that only one drop remains in the bottom. So you need to touch it once on the edge to get like a drop to come out, and then you'll see a little bit still in there. You don't blow that out or anything, that's it. So once you've done that, you then put 3 drops of your indicator in, phenolphthalein. No more than that because it's a weak acid, so it'll change your reading. It won't have any colour, it'll be clear. You put that, it looks like water under there, smells like vinegar though. And what you do then, I'll have to turn this to the side just so I can operate it, is, now you would be on a higher bench than this, so I'll just pretend that I'm standing. I always put my hand around the whole thing because I have a finer sense of control like that, but you may not. So you want to, if you're right-handed, you want to be swirling all the time and letting this in. But some people, right-handed people, prefer this. So whatever suits you, you do. So you want it to go, as I was saying to Stuart, your first one, you can be quite rough with. You find out where it changes colour, otherwise dropping one drop in from the beginning is going to be massively terrible. You can also tell once you've done a number of these how much roughly it is. So I can tell you the rough end point and you can get there. You write your rough down, and then the second time, say your rough end point was 24, take 2 off and go really fast down to 22 and then drop by drop till you get the very point that this turns the faintest pink. You can just see it. You've got to make sure it'll stay for 3 seconds because sometimes it'll turn pink and then disappear again. So you count to 3 and that's... If you're unsure of an end point, you take it anyway because you might find the very next drop turns it massively pink and you've missed it. So take a couple of readings. Anyway, I will be up there to help you, but that's how you do a titration.